Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problems 21 to 25 of the January 27 Algebra 1 New York Regents exam. Alright, let's take a look at question 21. It says a graph of average resting heart rates is shown below. So we have the graph here. The average resting heart rate for adults is 72 beats per minute, but doctors consider resting heart rates from 60 to 100 beats per minute within normal range. So the question is, using this graph above, which statement about average resting heart rate is not supported by the graph? Okay, so let's go ahead and write down the notation for the function that this graph represents. So let's say let a of x be the average heart rate for any age x. Okay, so let's take a look at the first statement. First statement is a 10-year-old has the same average resting heart rate as a 20-year-old. So let's test statement 1. What statement 1 is saying is that the output for 10 and 20, if inputted into the function, is going to be the same. But is that the case? Let's check out the first one, a of 10. A of 10 is basically the heart rate for a 10-year-old. Now, how do we use this graph to figure out the heart rate for a 10-year-old? What you do is you go from your inputs to the graph and then trace it to the output. Okay, so our input is 10. We trace it to the graph, hit somewhere there, slightly above 90, and then that's your output. So let's say it's like 92. Okay, so for a 10-year-old, it's 92 bits per minute. How about a 20-year-old? So for a 20-year-old, we'll follow the same procedure. We're going to trace 20 to the graph, and it already tells us nicely here that a of 20 is 72. So the output is going to be 72. So a of 20 is equal to 72 beats per minute. Are they the same? The answer is no. Okay, so option 1 is not supported by the graph. So why is that the case? Let's write this down. So option 1 is not supported. Why? Because a of 10, which is equal to 92, is not equal to a of 20, which is equal to 72. That's a false statement. Okay, so they do not have the same average resting heart rate. So our answer is option number 1 because we're asked to select the one that's not supported. Let's take a look at the other ones just to make sure we really understand this concept of using graphs to read out output values of functions with specified input values. Okay, so for option 2, it says a 20-year-old has the same average resting heart rate as a 30-year-old. So this statement must be true because we stated earlier that only the first one is false. Okay, so let's see if that's true. For number 2, a 20-year-old has what average resting heart rate? That's a of 20. We already know what that is. If we trace it to the graph as we did before, our output is going to be 72 beats per minute. How about a 30-year-old? A of 30 is the output when you input 30 into the graph. So this is 30 right here. It hits the same horizontal line. The output for this entire region from 20 to 50 is 72. So since 30 falls in that interval, a of 30 is 72 bits per minute. Okay, so this one is supported since a of 20 which is equal to 72, is the same thing as A of 30. Okay, so that's good. The next one should be supported also. It says a 40-year-old may have the same average resting heart rate for 10 years. All right, let's test that out. So for option 3, what's the resting heart rate for a 40-year-old? The average resting heart rate for a 40-year-old, I will go from 40 to the graph. We hit the same horizontal line. We have the same output of 72 beats per minute. How about in 10 years? In 10 years, what is the average resting heart rate going to be? So in that case, we're just going to compute A of 40 plus 10. A of 40 plus 10 is A of 50. What's the average resting heart rate for a 50-year-old? If you trace it up, you see that it's 72. Okay? 72 bits per minute. So, is this statement supported by the graph? Absolutely. How do we know it's supported? It's supported since the resting rate is what? Is constantly what? Is constantly 72 bits per minute from 40 all the way to 50. Okay, from 40 to 50 years. We have this horizontal line right here. The slope is 0, so that means the resting heart rate does not increase nor decrease, which means that it stays constant. Same means constant. Okay. Option 4. The average resting heart rate for teenagers steadily decreases. So if we're looking at increment or decrement, we're looking at slope. Okay. So decreasing indicates that the slope should be negative. So what's happening when we go from, what are we looking at? We're looking at the teen years, okay? From 13 all the way to 19. Okay, so let's go from 13 even to 20. So if we look at that interval from 13 all the way to 20, what's happening with the line? What's the slope of the line? The slope of the line is negative. So since the slope of the line is negative, that means that the heart rate is decreasing. Okay? Alright, so we just say the slope from 13 years to 20 is negative. Okay? Alright, so is that supported? Is this statement supported? Definitely. So this is supported for the same reason. Okay, since the slope of the line during the teen years is negative. Okay, if you have a negative slope, that means that the quantity is decreasing, and then if you have a positive slope, it's increasing, and if your slope is 0, that means it's constant, just as we talked about in problem 4, option 3, when we had the same average resting heart rate from 40 to 50 because the slope was 0, which indicates a constant average resting heart rate. Okay, let's take a look at problem 22. It says, the method of completing the square was used to solve the equation 2x squared minus 12x plus 6 equals 0. Which equation is a correct step when using this method? Okay, so one thing you want to remember, real quick reminder for completing the square. Reminder, when solving quadratics, by completing the square, ensure that the coefficient of x squared, which is basically a, is 1. Okay, you always want to make sure that that's the case before ever you start. So that's just a side point. So let's go ahead and do the problem. We have 2x squared minus 12x plus 6 equals 0. So if we follow the reminder here, we want to make sure that the coefficient of x squared, or a, is equal to 1. What is a here? The a value here is 2. That's no good. We need to fix that. How do we make the a value, or the coefficient of x squared, 1? We divide by the coefficient if it's not 1. So divide every single term by 2. Okay? If we do that, we have x squared minus 6x plus 3 equals 0. Alright, so now we're ready to complete the square. So to complete the square, we'll first create an incomplete square. Okay? So to do that, we're going to move the constant to the right. So subtract 3 from both sides. And that yields x squared minus 6x equals negative 3. So we're going to ask ourselves, what can we add to this incomplete square on the left side so that we have a perfect square trinomial? So what do we add here? Whatever we add to the left side of the equation, in order to preserve equality, we have to add the same number to the right side of the equation. Okay? Alright, so to complete the square, what do you add? To complete the square, you add b over 2 square. Okay? You have an incomplete square. To complete the square, you add b over 2 square. Now, what is b? b is a coefficient of x. b is equal to 2. Okay? Now, what do we do with that value? b equals 2. To create a perfect square trinomial from this term, we have to divide by 2, which is equal to 1, following that formula there, and we have to square it. Okay? So we have, okay, let's make a real quick correction. b is 3. It's not 2. b is 3. No, b is negative 6. The coefficient of x is negative 6. Alright, so we divide that by 2. So negative 6 divided by 2 is negative 3. And then we'll go ahead and square that. Okay? So square that, we get positive 9. So that's the number that creates a perfect square trinomial on the left side. So we add a 9 here. And since we have an equation, to preserve equality, we add a 9 on the right side. Now we have a perfect square trinomial. To factor this, what we're going to do is we take the square root of the first and the last term and bring down the middle sign. Okay? Alright, so if we do that, we're going to have x minus 3 quantity square equals negative 3 plus 9, which is equal to 6. Okay? So this is where we're going to stop, because if you look at the options, this is the extent to which they went when they're trying to solve the quadratic. Okay, so let's see which one is the answer. X minus 3 quantity square equals 6. The correct answer for number 22 is option number 1. Alright, let's take a look at question 23. It says Nancy works for a company that offers 2 types of savings plan. Plan A is represented on the graph below, so we have the graph. And then plan B is represented by the function f of x equals 0.01 plus 0.05x squared, where x is the number of weeks. Nancy wants to have the highest savings possible after a year. Nancy picks plan B. So, question, her decision is 1 correct because plan B is an exponential function and will grow faster. 2, her decision is correct because plan B is a quadratic function and will increase at a faster rate. 3, incorrect because plan A will have a higher value after a year. And then 4, incorrect because plan B is a quadratic function and will increase at a slower rate. Okay? So, just a side point to keep in mind. The higher, let's just put a tip. The higher the degree of a polynomial, the higher the degree of a polynomial, that the faster the growth rate is. Okay? Higher the degree of a polynomial, the faster the growth rate. Okay, so what we're doing here is comparing this linear function with this function right here. So let's call this plan A. Let's call it g of x. Okay, plan A, which is g of x. What kind of function is this? It's a linear function. Okay, g of x is a linear function. So what does that mean concerning the degree? With degree 1. All linear functions have a degree of 1. Okay, how about f of x? F of x is the highest degree is 2. F of x is a quadratic function with a degree of 2. Okay, so you expect a quadratic to grow faster, but it also depends on where we start. Okay, alright, so let's take a look at the options. Option 1 says that plan B is an exponential function. Is that correct? That's wrong because plan B is a quadratic. Okay, so how do we know which one is greater after a year? Okay, so if we have a year, how many weeks is that? You have 52 weeks in 1 year. Okay, so what we're doing next is comparing the outputs when x is equal to 52 for these two functions. Whichever is bigger will tell us if Nancy's pick is correct. Okay, so let's start with g of 52. Using plan A, what is the output after 52 weeks? What's her balance? Okay, so using plan A, we have g of 52. So what we'll do is we're going to go to our graph. We're going to input 52. So this is 50. Every tick mark is 2, so we go 52 right here. And then trace it to our output. It's kind of in the center between 100 and 110. So g of 52 is kind of, let's just call it 105. Okay, 105. What's the story with plan B? For plan B, we have f of 52, but we know what f of x is, right? F of x is 0.01 plus 0.05x squared. So what are we going to do with this? We're going to input 52 for x. Okay, so we have 0.01 plus 0.05 parentheses 52 raised to the second power. Okay, so let's go ahead and enter that into our calculators. So we're going to have 0.01 plus 0.05 times 52 raised to the second power. Okay? Enter. We get 135.21. 135.21. So which one has a higher amount? Clearly, plan B has a higher amount. So, back to the question. Is Nancy's decision correct or incorrect? Nancy's decision is correct, okay, because we have a bigger savings balance using plan B as opposed to plan A. So we eliminate 3 and 4. Our answer is option number 2. Let's write down a statement real quick. Nancy's decision is correct because plan B yields 135.21, which is greater than what? Which is greater than plan A, which yields what? Which yields just $105. So her decision is correct. All right, let's take a look at question 24. It reads, the winner of the Boston Marathon runs as many as 120 miles per week. During the last few weeks of his training for an event, his mileage can be modeled by m of w equals 120 times 0.9 to the w minus 1, where w represents the number of weeks since training began. Which statement is true about the model m of w? All right, so let's do a real quick review on exponential growth and decay functions. Okay, so an exponential function can be given by f of x equals the initial amount a times 1 plus or minus r to the t. Okay, so f of x basically yields the final amount. Okay, so let's see how we can apply this formula to this scenario. Now, we can split this formula into two cases. One is decay or decrease, and the other is growth. Okay, so we have a exponential decay scenario where basically the amount of increment decreases with time. In that case, we have f of x equals a times 1 minus r to the t. Okay, so you have 1 minus r. Now, in the other case, we have growth. In that case, we are going to be having an increase. Alright, so in that case, we have f of x equals the amount times 1 plus r to the t. Now, do you see the difference in these two formulas? You have 1 minus r for decrease, and then you have 1 plus r for increase. Okay? Alright, now let's take a look at this formula that we have here. We have m of w equals 120 times 0.9 raised to the w minus 1. Now, is this a decrease or an increase exponential scenario? The key is to look at the quantity that's been exponentiated. We have 0.9. How does 0.9 compare to 1? If the quantity in the parentheses is less than 1 and greater than 0, of course, we have a decrease, exponential decay. But if it's greater than 1, we have an increase. Okay? So here we clearly have a decrease. Let's put it down. We have an exponential decay Decay means decrease, okay? Exponential decay since the quantity in the parenthesis 0.9 is less than 1, okay? So what is the decay rate in this particular case? What is the decay rate? So to figure out what the decay rate is, we're going to use this formula up here. We have 1 minus r, the quantity in the parentheses, equals 0.9, okay? So let's solve this for r. If we want to solve this for r, we can subtract 1 from both sides, 1.0. What do we get when we carry out the subtraction? When we carry out the subtraction, we get negative r equals, now we can, we're going to subtract and keep the sign of the bigger, okay? So if we subtract 0.9 from 1, we get 0.1, but since the bigger is negative, we have negative 0.1. To get r by itself, we divide both sides by negative 1, and we have a decay rate of 0.1, which is equal to 10%. Okay? So what does this mean? Let's put this this growth rate, within the context of the problem. This basically means that the number of miles he runs decreases by 10% each week. Another way to express a decrease of 10% is basically saying that, or the mileage of each week is 90% of the previous week. Okay, so these two mean exactly the same thing. When you're decreasing something by 10%, the resulting amount is going to be 90% of the original amount. Okay, so with that in mind, let's look at the options and see which one is correct. So the first option says the number of miles he runs will increase by 90% each week. Look at this word increase. Are we looking at an exponential growth or decay scenario here? In this particular problem, we have a decay scenario because the rate is less than 1. Okay? Each week is going to be 90% of the previous week, or a 10% decrease from week to week. So option number 1 is wrong because the model is a decay model. Okay, because the decay rate, the rate of growth or decay is less than 1. Option 2, the number of miles he runs will be 10% of the previous week. This is incorrect. Each week will be 90% of the previous week. Okay, that's equivalent to a 10% decrease. So the number of miles he runs will be 10% of the previous week. That's wrong. It's supposed to be 90% of the previous week. That is what the resulting impact of a 10% decrease will cause. Okay? Now, let's take a look at option 3. M of W represents the total mileage run in a given week. So what does this function tell us? If you go to the problem, the function tells us that M of W represents the mileage that he covers for the last few weeks. So this is exactly what M of W is. Remember when we talked about the function basically yields the final amount after a given time. Okay, so our function right here gives the final amount after a given week. So option number 3 is the correct answer. What's wrong with option 4? W represents the number of weeks left until the marathon. Let's go back to the problem. The problem states that W represents the number of weeks since the training began. So we can see that option 4 is clearly wrong. Okay, so let me give you a visual to help you understand what's going on here. Let's say we have a number line. Okay, and this is the marathon right here, and this is the start of the training. Okay, start of the training. Start of training. Now the question is, what does W represent? W represents the number of weeks since the training began. So if we put W somewhere here, or if we mark, let's say, somewhere here for a certain number of weeks, this is what W represents, the distance from the start of the training. Okay, and option 4 is telling us that W represents the distance until the marathon, which is incorrect. This is what W represents, the number of weeks since the training began. So we can clearly see that our answer for question number 24 is option number 3.